Thank you for attending today's presentation, and today we'll be talking about ligand cross-linking of quantum dots for nano-patterning of future display technologies. So let me give you some background and motivation. In past few years, we have seen that our displays have gone much sharper, much brighter, much higher resolution, and that for that we need to have a much higher pixel per inch or PPI density. Uh, and as we are going with VR and AR headset, which are very close to our eyes, we need much more pixel per density. And the conventional technologies are coming to a saturation point, and we need some alternative display technologies that can make this possible. One such example is the quantum dot display market, which you might have seen in recent times because of Samsung, which launched their quantum LED TVs, which are much sharper, much brighter, much more energy efficient. And the market is going to be increasing in the next decade, and this has increased a lot of interest for quantum dot manufacturing and display technology, and we'll be talking about that today. Let me explain you what exactly these quantum dot technology display technologies are. So quantum dots are nothing but very small nano crystals of a certain semiconductor. In this case, it can be CDSE or it can be perovskites, anything. And the best thing about them is you can control their color based just on their size. So you can have different sized, small size crystals in nanometers, and you can control their size. And they're very, very bright. Here is an example of how you can make these quantum dot LED TVs, and you can have these quantum dots arranged or patterned in a certain RGB way, which is an industry standard, which will comprise the display, and you can have a very fine screen. But how do you make these patterns, and what manufacturing processes can be used in these things? One very well-established option is to use lithography, which is a very well-established technique for semiconductors, which is nothing but you use a certain mask and a photoresist to pattern or to make the pattern you want for your semiconductors. So we can use the same thing for quantum dots, where you can have a certain mask, a photoresist, you can deposit your quantum dots, and then you have a developing process, which means that you etch away or sacrifice the photoresist, and you have this pattern. And we can keep on repeating this to create this RGB structure. However, because the quantum dots are much less stable and they themselves gets dissolved in the solvent, it's very difficult to have this patterning using the photolithography step. So we need something else that we can take into account. So that's why our collaborators at South Korea have come up with a photoresist-free lithography step. So basically what they did was the quantum dots which we use have certain ligands on their surface, which are nothing but alkane chains. And these, if you can try to make these ligands stay together and cross-link together, you can keep these two quantum dots stay together, and they are much more stable, they don't get dissolved. And that's the same exact technique our collaborators used while creating these different patterns on the substrate. So for example, you have your quantum dots uh, and you deposit them on a certain substrate. You can irradiate them with light, create the patterns you want, and the cross-linkings are light reactive. So they form these cross-linkers once they're exposed to light, and the quantum dots stay together, and you can have these RGB quantum dot pixels, or you can have this pattern. To explain how this cross-linking works, as I mentioned that the quantum dots have ligands on their surface. So if you can bind these ligands with one another, you can keep the quantum dots together. And once they are together, they are much more stable. They don't dissolve while making these patterns, and you can do this repeated patterning of RGB pixels that you want. You can also have different kind of these likesers or cross-linkers, as we call. So there can be just two cross-linking agents, which is called two likesers. There can be four cross-linking agents, which can be four likesers. So you have four positions where you can cross-link. Or you can have a six likesers where your molecule has six binding positions where it can cross-link with six different ligands at the same time. Here is a snippet of some experimental observation. So if you do not cross-link these quantum dots and try to develop them, they just get dissolved. As you can see here, the red becomes black, so there's no red quantum dots. But if you cross-link them, the ligands stay together, the quantum dots stay together, they're much more stable, and then you can have this film and you can try to repeatedly pattern it. This is all from experiments, and however, it's important to understand how mechanistically this cross-linking reaction is happening and what are the different effects to understand and make it better. And for this purpose, we are using kinetic Monte Carlo or kMC simulations, which is nothing but a tool of how to model microscopic reactions or mesoscopic reactions on very small surfaces. So let me better explain the cross-linking reaction and the kinetic Monte Carlo simulation. So basically we have our cross-linkers, which are nothing but azide moieties, which have two azide nitrogens on it. Once they get exposed to light, they form these nitrines, which are very reactive. And these nitrines can then react with the carbons on the ligands and try to form a crosslink. So with this crosslink, now these two quantum dots are staying together, which means they are much more stable and they do not dissolve, and you can create these patterns. In a kMC simulation, we can break this down in various reactions. So for example, the first reaction would be to form the radical. So we can have a radical reaction and write a rate for it. Secondly, these nitrines can now form the crosslink, or they can do a CH insertion reaction. So we can have a reaction constant or reaction rate for this cross-linking reaction. Also, when they are choosing where to cross-link, they have various options. They can choose this carbon, they can go on the left side, or they can go on the right side. So we have to spatially consider all these possibilities in our simulation. So here we have a schematic of how your kinetic Monte Carlo lattice will look like. You already have your quantum dot surface, you have your red ligands, and these blue cross-linkers. And what we are going to model is how structurally and with temporally they kind of form these bonds and cross-links to do the cross-linking reaction. I mentioned about different kinetic Monte Carlo rate laws, and here is a compilation of the rate laws we have used for the radical reaction, for the cross-linking reaction in the simulation. Another important thing to consider is the steric effect, which means that if you have a big LICER or a big cross-linker like this 4 cross-linker, which is tetrahedral in shape, and it forms this cross-link between two ligands, and if another cross-linker wants to come here and bond over here, it's going to face some steric effect. So to account for this, we created an energy barrier called EA, which is the steric energy barrier. And it also depends upon what are the neighbors it has. So this is pretty crowded, so it's going to have a very high energy barrier, and that decreases the probability of this cross-linking happening over here. Maybe it can happen over here, which is a much better spot. Once we have these all rates, all these steric effects, we can write a kMC simulation algorithm, which is, to explain briefly, we initialize our lattice, kMC lattice. We calculate the rate of all these reactions. We choose the desired reaction. We update our lattice, and we keep on doing this. So let's look at some results. As I mentioned, the kMC lattice is nothing but a numerical 3D matrix. So this is our quantum dot surface. This in the Z direction is our ligands. And here you can see a snapshot of these red dots. These are the ligands which are cross-linked with each other, and we can trace this evolution over time. Here are the results for 2 LICER. That means you have 2 azide moieties for the cross-linking. So initially your cross-linking is 0. That means no ligands are cross-linked. And as you proceed with time, eventually you saturate to a value where all the cross-linkers have been consumed, and they have cross-linked the maximum ligands that are possible. The y-axis here, which talks about the percentage cross-links, is nothing but the total cross-links that are formed divided by whatever the total crosslinks you can form hypothetically are. On the other hand, when you have 4 LICERs, that means the cross-linking moiety can have 4 azide bonds which can cross-link with different ligands. Your cross-linking percentage is much higher. It's around 12% as compared to 6%, which means that a lot of ligands in a neighborhood are getting cross-linked, which is good for us. Similarly, if you look at 6 LICER, that means you have 6 azide moieties, your cross-linking percentage is even much higher. It's 18%. And here is a time varying schematic where initially you have very less crosslinks, and then as time proceeds, the crosslinks keeps on getting larger and larger, and they are connecting the ligands in the small neighborhood to form like small ligand clusters and hold the quantum dots together, which is better for us. Here is a comparison of using these different likesers. So 2 likesers, 4 likesers, 6 likesers. So we have the same amount of these cross-linkers, but each of them have very different moieties. And you can see 6 likesers and 4 likesers are much more cross-linked, much denser in their cross-linking as compared to 2 likesers, which is expected and makes sense. I mentioned about the steric effect, where I said that if a bulky liker like this is already bonded and other liker wants to come in the vicinity and bond there, it's difficult, and we have this energy barrier. So we studied how this steric barrier is going to affect the cross-linking. When you have a very low steric barrier, it really doesn't make a difference. So the blue curve and the red curves are for the steric and no steric case, and even for 6 likes it doesn't really make a difference. But however, once you go to a higher steric barrier, you will see that that because of the steric barrier, the cross-linking has decreased, and it's difficult for 6 likes because of its large steric hindrance to bond with the neighboring crosslinks. On the other hand, when you look at 2 likes, which is a simple linear molecule, uh, the steric barrier does not have any effect, and this is because the 2 likes it's a very small moiety, and it does not have a major steric effect. So the main takeaway from this work is even if you have the same amount of or same weight percent of these likesers or cross-linkers, um, if we have a 6 liker, which means a cross-linking with 6 cross-linking moieties, your cross-linking efficiency is going to be much higher. So here is in a comparison of 2 moieties, 4 moieties, and 6 moieties. And for, even if you have the same 10% weight of these likers, the 6 liker cross-links at a much higher level as the as 2 liker. Finally, let's look at some conclusions and some future ideas we have. So I talked about cross-linking and the steric effect associated with, but I did not talk about the steric transport effect. So what I mean is, if we have this 2 liker, which is this linear small molecule, and these are 2 ligands, it can easily penetrate and go and bond with anything. On the other hand, the 4 liker, which is tetrahedron, might feel a bit difficult to go inside these ligands. The 6 liker, which is a much bulkier molecule, is going to find very difficult to even go inside, and maybe it bonds only here. And this is a much difficult simulation to do, and we need high fidelity studies. Uh, One of the ideas we have is to do MD simulations to calculate something we call as inclusion energy. So what that means is basically you have your ligands, you have your quantum dot surface, and you have your likes. And as the likes keeps on going inside the ligands, it's going to increase. Your inclusion energy is going to be unstable. And then we can calculate how this inclusion energy increases for 2 likes, which is a linear molecule, for 4 likes, for 6 likes, which are much bulkier molecules. There's another approach where we can use Langevin simulations, which are nothing but a discrete element method where you apply Newton's laws of motions for each of these particles to calculate how the size affects this cross-linking, and how well they can go inside this ligand structure. So finally, I want to summarize and say, in this work, we developed a kinetic Monte Carlo model to understand how the cross-linking uh, between 2 quantum dot and ligands work for nano-patterning applications. As expected, we found that the higher your cross-linking moieties are, for example, 4 likes or 6 likes, which are much bulkier, have much more multi-pocket cross-linking abilities, your cross-linking efficiency is much higher. However, they are also much more prone to have that steric effect where they're going to be sterically hindered. In the future, we are going to be looking at the sterically hindered transport that I talked about using MD simulations. We will use this uh, idea of inclusion energy to kind of find whether it's really possible for the 6 light cells or 4 light cells to penetrate the surface, and a dedicated study will be done in the future. With that, I want to say thank you, and I'll be happy to take any questions if you have. Thank you for attending.